Hello, my name is Stanley Grant, and I am the director of the NSF Partnerships for International Research and Education program at University of California, Irvine, or UCI. And I wanted to welcome you to kind of an innovative series that we're putting together in which what we're trying to do is bring together some of the world's experts in green infrastructure, stormwater infrastructure, and have them talk about various aspects of these systems from their particular expertise. And so what I wanted to do today was give you a really broad overview of our program and some of the things that we're thinking about, and really hopefully contextualize green stormwater infrastructure for you so that the more specific talks can be kind of placed into a broader context. So, the broad context of our work is really envisioning a new type of city, which we call a water-sensitive city. And I'll be, as I go through the talk, I'll be explaining exactly what I mean by that. So here's a brief summary of our NSF Partnerships for International Research and Education program. It's entitled Low Energy Options for Making Water from Wastewater. And as I said, it's funded by the National Science Foundation. It's about a $5 million grant. And let me tell you a little bit about the PIRE program at NSF. It's the only program at NSF that is specifically directed toward international research and education. And it's pretty much across all areas that the National Science Foundation funds. And so we were very lucky to get one of the PIREs, again, focused on the issue of essentially using our water better in cities. And the title of that project, again, is Low Energy Options for Making Water from Wastewater. And the hook that we had for our particular proposal was that Australia, and in particular Southeast Australia, went through about a 12-year period of low precipitation or drought, which was called the Millennium Drought. And during that period of time, they implemented a lot of policies, they changed their infrastructure, they had a lot of innovations that they implemented. And the hook of the proposal was we might be able to learn something from what Melbourne did during the Millennium Drought and bring it back to the US, where we have our own concerns about long-term water supply, particularly in the Southwest US. And so, so that was kind of the hook. Again, the program itself is centered at UC Irvine, but we have a lot of partners. So we're partnering with ecologists at UCLA and Scripps Institution of Oceanography. And also our research partners in Australia come from the University of Melbourne and Monash University. And so through the video series that hopefully you'll watch, you'll hear from folks from both of those universities as well as the US side of the ocean. So anyway, with that kind of overview, I want to tell you a little bit about the context of a water-sensitive city. And really, you know, I'm an engineer, and when you think of sort of from the, if you think about the world as an engineer, it's fairly narrow. You know, you've got a problem, you're trying to fix it, you design a solution, and you move forward. But in the broader context, we're part of an evolution, we're part of a history. And I think it's hard to see ourselves in that context. And so in that way, it's really helpful to turn to social scientists who really do think about the evolution of cities and the evolution of disciplines. And in this regard, Professor Rebecca Brown at Monash University has done some very nice work looking at sort of how cities evolve with respect to their what's called hydrosocial contract. And what I mean by hydrosocial contract, or what she means by hydrosocial contract, is essentially a contract between the citizens of a city, that's the social part, and the government leaders, I guess that's the hydro part, regarding the supply, conveyance, and other factors surrounding water. And so her idea is this hydrosocial contract between the people and the government evolves over time. And we can kind of see that evolution actually looking maybe kind of locally. Here, UCI is in Southern California, and so it's easy to look, say, to Los Angeles, which has a very interesting water history. You know, you probably have read about it, or perhaps you have seen movies like Chinatown, which have dramatized that rather sordid history in LA. But anyway, let's kind of walk through her idea of the evolution of the hydrosocial contract and see how it might fit in to a place like Los Angeles or Southern California. So her idea is that basically when cities begin, they really are water supply cities. That is, the hydrosocial contract, which is the top box, is essentially all about guaranteeing water supply access and security for the population. In other words, the citizens expect the government to provide the citizens with limitless sources of water. So that's the hydrosocial contract. And then the engineers come into that because they actually have to make that happen, right? And they provide the technical know-how, which for this particular hydrosocial contract comes down to supply hydraulics. So it's all about hydraulic engineering. So we have the hydrosocial contract at the top, which is essentially driving the investments and technology and know-how. And then we have the supply hydraulics, which is the actual implementation of that hydrosocial contract. And so you can see the hydrosocial contract at the top and the engineering tools at the bottom. And so this is what Rebecca would say about the hydrosocial contract for water supply cities. She would say it implicitly promised the delivery of a safe, cheap, and largely limitless volume of water from a benign environment to the rapidly growing urban population. And if you think about Los Angeles, basically that hydrosocial contract, the water supply city, is brilliantly summed up in William Mulholland's statement when he first opened the LA Aqueduct in 1913, November 5th. He said, "There it is, take it." He was a man of few words. And essentially in those few words, he embodied that idea of a water supply city. We will provide the water, you take it and use it. And so as cities then begin to develop, they have a secure source of water, and so their populations begin to grow, then another concern becomes prominent, and that is public health. Certainly back in the 1800s, 1700s, 1800s, this manifests as horrible epidemics of disease, most particularly cholera. And so basically the idea here is we'd like to change or evolve our hydrosocial contract. The citizens demand a change in the hydrosocial contract, so it's not just about water security anymore, it's about public health protection. So that's the top box there. That's the change in the hydrosocial contract. How do we implement that? Well, we task the engineers with going about and building sewer systems, which by and large are gravity drain systems using the same kind of physics, hydraulics, hydraulic engineering that they use to develop the supply hydraulics. So they're really using the same tools, but they're adapting them now to the development of sewer systems, which were all about moving sewage away from the city. Just like in the first case with water supply city, it was about moving the water to the city. And then as you can see on the slide here, the next thing that people begin to worry about is flood protection. And there's a lot of reasons why this comes about. It's actually due to a fundamental change in the hydrology of cities as they grow. To sort of make a very short story out of it, what happens when a city grows is that it essentially replaces or terraforms an area, removing trees and grass and replacing the trees and grass with impermeable surfaces. And this has really profound impacts on the local hydrology. In particular, most of the water that rained in a natural catchment would go back to the atmosphere as evapotranspiration. But if you replace those trees and grass with pavement, which doesn't evapotranspire, that water is just going to sit there. So what used to go right back up into the atmosphere now is going to sit on the ground. Worse than that, we've created these impermeable surfaces so that extra water can't infiltrate into the ground. And so if it can't infiltrate into the ground and it can't go back into the atmosphere, you can guess where it's going to go. It's going to go into your homes, your businesses, and so forth. And so suddenly, just by creating the city landscape, we've created tremendous risk for flood protection. We brought people into a region, and then we've altered the hydrology in such a way that it puts them at great risk of floods. And so the response then is the citizens demand that the hydrosocial contract yet again be evolved to include flood protection. And so once again, we bring in the engineers and we have them design a drainage system which moves that stormwater as quickly as possible from the city to a receiving water. And so everybody's happy with that, I guess, except for the fact that all of that runoff that we're moving very quickly to receiving waters actually has two bad things associated with it. The first is that the receiving waters, we're talking about rivers and lakes and coastal oceans, are not used to receiving the volume of water that we're sending to them. Remember, most of the water went up as evapotranspiration. Most of what was left was infiltrated and very slowly through the ground moved to local streams or coastal ocean. Now suddenly we're delivering a much larger volume of water and we're delivering it much more quickly to these sensitive environments. And all of the organisms, the ecosystems that have evolved there are not evolved to deal with all of that extra water. And so the net result is that you have a lot of ecological damage. Added to that is the fact that that stormwater runoff also contains a lot of pollutants from the urban landscape. So you actually have this kind of deadly 1-2 punch where you're delivering a lot of volume all of a sudden to sensitive receiving waters, and that water is also very polluted. And so that really leads to a new social, or an evolution of the hydrosocial contract, which I think one can actually look in time and identify a sort of point in time, almost globally, where awareness of the impacts of our drainage systems on the environment became really important. And that was during the 1960s, when suddenly there was an awareness that environmental protection was a really important part of what humans should be thinking about. And so now we evolved that hydrosocial contract again to add on top of it the social amenities and environmental benefits that we would like to have, and so thinking about ways in which we could protect that. That led to the formation of the Environmental Protection Agency in the US and in many other countries, similar kinds of organizations that were essentially intended to protect waterways from the pollution that cities, by and large, but of course other areas too, were generating. And so the addition of the social amenity or environmental protection on top of that hydrosocial contract sort of gives way to the waterways cities. And our engineering tool that we use to address that particular challenge is in a way fundamentally different than the ones that came before. Instead of just using hydraulics, which is really what the supply hydraulics and the sewer systems and the drainage channelization were all about, now we have to bring in chemistry, we have to bring in ecology. And so this was also a renaissance period actually in universities where suddenly people started thinking about not just the flow of water, bringing it to or from a city, but also the chemistry and the microbiology and the ecology of receiving waters. And in particular, how best to manage point and diffuse source pollution. And what we're beginning to experience now, so that was probably a transition that occurred again starting in the 1960s through the 1970s, even to when I got my Ph.D. in the early 1990s, that was kind of the dominant paradigm. But what we're finding now is a new evolution. Actually, this isn't just an evolution in a particular city like Los Angeles or Melbourne, Australia. It's very profound. Some scholars refer to it as a new epoch in human history, where instead of us always looking for the highest quality source of water, or maybe bringing water, high quality water from a long way away, we're essentially tapping that out. We're running out of those high quality water sources. And so what we're doing now is we're actually tapping local sources which are not so high quality. So that's the genesis of wastewater recycling, for example. Our particular project, this NSF PIRE project, is really interested in green stormwater infrastructure which captures and uses stormwater runoff, which is another type of low quality water. So all of these activities to try to capture local sources of water and use them are really fundamentally new type of phenomenon in human history. And they all come about from an understanding that there are limits on natural resources. So our hydrosocial contract is now being evolved again to recognize those limits. And the engineering tools that we need to bring to the table to address that hydrosocial contract are again a major evolution because they are so interdisciplinary. So now not only are we thinking about flow and ecology and microbiology and chemistry, but we're also bringing in landscape architects, or we're bringing in social scientists who think about how people fit into the equation. And so we're really looking at, from an engineering perspective, designing and building diverse, fit-for-purpose water systems. That is, systems which deliver water which is fit for the purpose that it's intended. For example, we don't need to use potable water to flush a toilet. We could use mostly purified stormwater instead. And also conservation of waterways and protection of waterways is part of that story. And you can see that happening in Los Angeles. So exactly 100 years from the day when Mulholland famously said, "There it is, take it," Eric Garcetti, the mayor of Los Angeles, went back to the same spot and he said, "There it is, conserve it." So again, you see over that 100-year period of time, a complete evolution in the Hydra social contract as recognized by the key leaders at the 2 points of time. What does the interconnection of these different water systems look like? This is a rather complicated graph, and I kind of apologize for that, but it's really interesting. It's one of the few that I've seen that's really summarized, sort of a snapshot summary of all of the water systems in a large metropolitan city. And in this case, it's the annual water budget for the city of Melbourne in Southeast Australia. And I'm just going to kind of walk you through the boxes and then talk about the things that are going on in the city that could ultimately result in really big changes in the way that this water budget looks maybe 50 years from now or 100 years from now. So Melbourne is kind of a unique city. It's a beautiful city. I hope you get a chance to visit it sometime. And one of the things that's really unique about it is it sources almost all of its water from protected catchments. New York does something like this too. The idea is that the city essentially owns, or the water agency, Melbourne Water, owns large swaths of the catchment area, and they fence it off from the public. So the public is not allowed to develop it or live in it, graze cattle in it or anything like that. It's protected. It's a protected catchment. And the idea is that because it's a protected catchment, there is not a lot of pollutant generation. And so the water that comes out of that catchment essentially flows into a series of reservoirs, and then with very minimal treatment is essentially distributed to homes through reticulated water supply. So, so that you can think about that system. It's really brilliant in two ways. One, it's driven by gravity, right? So the water falls in the mountains and it flows through the catchments into reservoirs and then flows downhill to the cities. So it's actually very energy conserving. And the second thing that's brilliant about it is because there aren't a lot of people living in the catchments, there isn't a lot of pollutant generation, and so you don't have to build a lot of centralized infrastructure to remove pollutants before you deliver it to the people. So, so both of those factors make this an extremely energy efficient and environmentally friendly system. We could learn a lot from that. The size of the boxes that we're seeing on this particular graph indicate or some representation of the volume of water associated with each component of that system. So for example, the total inflow from the catchments is about 844 gigaliters. Well, let's talk about a gigaliter for a second. A gigaliter is 10 to the 9th liters, so it's a billion liters. To kind of give you a sense of what a gigaliter would look like, if you were to see it walking down the street, a gigaliter is about the amount of water that you would need to fill 400 Olympic-sized swimming pools. So it's a very large amount of money, well, money too, it's a very large amount of water. And so the total amount of water coming in from the catchments is 844 gigaliters in this particular year, in 2010. And that's so almost about 1,000 gigaliters of water coming into the system. So 2010 was a good year for Melbourne. So they actually were able to capture some of that water and store it, kind of put it in the bank. And so the box on the right there indicates that of that 844 gigaliters, about 300 gigaliters went into storage. Most of the water, about 356 gigaliters, went to the city of Melbourne, where it was consumed. Actually, a little more than 356 gigaliters was consumed because there were other sources of not high quality water which contributed to the total consumption. So we have a total consumption in Melbourne, that box that I'm pointing to now, of about 412 gigaliters, a little bit more than the amount of water that was supplied from the protected catchment. Of that, about 297 gigaliters was converted into wastewater. You flush your toilet and goes into the sewer system, which then went to the wastewater treatment system. And so the wastewater treatment system basically treated about 315 gigaliters of water, again during 2010, of which about 220 gigaliters was discharged to essentially Port Phillip Bay, which is the bay that leads to the ocean adjacent to Melbourne. Some of that water, just a little bit of it, was used for what we call environmental flow. That is to support environmental systems. So some of the treated wastewater went to one of the lakes, where essentially it was used for supporting ecosystems and wildlife and so forth. Now, I mentioned that we're in a new epoch in human history where we're beginning to sort of connect these systems which used to be very linear. You can see the vestiges of the linear system here, right? You start up at the top with this huge volume of water coming in from the protected catchments. Most of it goes into the city for consumption, and then most of that goes to the sewage treatment plant, and then finally it's discharged to the ocean. It's sort of a one pass-through system, and that was the vestiges of those old hydrosocial contracts. But now what's happening, and will happen to an increasing degree in the future, is that we're beginning to see arrows looping back upstream into the system. So for example, some of the wastewater that's treated in that bottom box is now being looped around back into total Melbourne region consumption. And so that's the little blue slice of the pie there. And that is usually used for things like irrigation of parks and so forth. There's also another box which I haven't really talked about, but is extremely important, and that's the amount of volume of water, 463 gigaliters, a huge amount of water that's generated as runoff from the city's pavement and impervious surfaces. So in fact, if you compare it to the total inflow from the catchments, it's actually over half the total inflow from the catchments. Where does that urban runoff go? Well, 453 of the 463 gigaliters gets discharged directly to rivers, streams, and Port Phillip Bay. And as I mentioned, not only is that a waste of water, but it's also very harmful for the ecosystems that are not used to the volume of stormwater they're receiving, nor are they used to the pollutants that are generated from it. And so what I want to point out is that there's a tiny little sliver of water in that urban stormwater runoff, which is in 2010 was being used for total Melbourne regional consumption. And so basically what was happening is that in part due to the millennium drought, they started to build, the city of Melbourne started to build green stormwater infrastructure which would capture some of that runoff and then recycle it for fit for purpose activities like, for example, irrigating parks and ultimately, in probably more small scale, flushing toilets and the like. The main thing I want to point out is that as time goes by, these activities, which we're just beginning to see the transition now, these activities of sort of reconnecting these usually very linear systems, looping them back, is going to happen more to a greater and greater extent. And our particular project, the goal really is to provide the science and engineering technological expertise to accelerate that process or make it happen more smartly. The same kind of vision of urban water systems as being really an urban water cycle is cropping up all over the place. And so here's an advertisement from Tucson Water in which essentially they are also acknowledging the fact that as opposed to the one pass-through system we used to have, that really all of our different water sources or water systems should be connected or are becoming connected. And that's really the right way to go if we're going to try to support the populations that we need to support, particularly in the face of climate change. So are we at the end of that hydrosocial contract evolution? Well, Rebecca Brown would argue no. She would argue that the next phase, which no city in the world has achieved yet, is what she calls a water-sensitive city. And a water-sensitive city is basically taking all of those great things that we're doing, the reconnecting the various kinds of water, using water more efficiently, and taking it to the next level. So we begin to think about things like intergenerational equity. How are the decisions that we're making today about our water going to affect, my children and their children, and so on? So are we locking ourselves into a path that could be maladaptive, could lead to problems down the road? I don't think we tend to think of it in that kind of long-term frame. We tend to think more in terms of political cycles, So who's up for president? And that changes every 4 years. So it's very difficult to transition, especially in a democracy. I think it's very difficult, not that I'm arguing for no democracy, but it's very difficult to sort of have these very, very long-range plans which maybe look 50 years or 100 years in the future and ask, how are the decisions we're making today going to set us up for a better future? And now we're really talking about an evolution of that diverse fit-for-purpose infrastructure into adaptive, multifunctional infrastructure that reinforces water-sensitive behaviors. And so again, the engineers are going to be required to take on a deeper understanding of how these systems should look and maybe a sensitivity to the diversity of opinions that have to go into their design. So that's really, in a nutshell, hopefully, the concept behind a water-sensitive city and how our project really connects with that. I want to give you a few examples, specific examples of technologies that we're focusing on in collaboration with our colleagues at Monash University and University of Melbourne. One form of a green stormwater infrastructure that we're quite interested in is a technology that's called a biofilter. It's actually really simple. Some people call them rain gardens. And the idea is that basically they're vertical, kind of like vertical wetlands, in which you have essentially a layered system with maybe sand, fine sand at the top and gravel at the bottom. And these are planted, and water, say stormwater runoff from roads or runoff from roofs, comes into the top of these systems, slowly percolates through the filter, interacts with the plants and the microorganisms and the animals that live in these systems, and then eventually reaches the bottom, and then the effluent can be used directly for fit-for-purpose activities such as toilet flushing again or irrigation. And so these, if you sort of look at it in a little bit more detail, these biofilters can actually be configured in a couple different ways, and we're going to explore this issue a bit later, but really is important in terms of thinking about restoring the hydrology of cities. So ideally, we would restore the hydrology of cities so that it was more like the pre-urban state, so we don't have the impacts on the receiving waters and ecosystems. So the neat thing about the biofilters is that we can actually kind of tune them to achieve exactly what kind of hydrological balance we want. For example, we could actually make them bottomless so that the water that filters through them actually infiltrates into the ground and supports shallow groundwater and then also base flow in streams. Of course, some of that water that's filtering through the biofilter is going to go up as evapotranspiration back into the atmosphere through the action of the plants. We call anytime you try to keep the water out of the watershed, or essentially export it out of the watershed, and that could be moving it back into the atmosphere or maybe moving it to the sewage treatment plant, we call that harvesting, whereas if we allow that water to infiltrate and support groundwater or shallow groundwater, we call it infiltrating. So we see from this particular configuration where we don't have a bottom to the biofilter, there's some harvesting, that is some of the water is going up as evapotranspiration, and we also have some infiltration, water's going down into the groundwater. Alternatively, we can put a hard bottom at the base of the biofilter and then essentially capture the water that infiltrates, the clean water that infiltrates through these systems, and then pump it maybe through some additional treatment, UV treatment, disinfection or something like that, and then pump it back into the home or use it, store it, use it for irrigation and that sort of thing. And this would be another form of harvesting if you think about it, because if we take that water and we bring it back into the home and we use it for toilet flushing, where does it go? Well, ultimately it goes into the sewer system and it goes through the sewage treatment plant, and then long time into the future it ends up getting discharged probably back to the ocean or recycled back into various forms of water use for the city, for example, secondary treated effluent for irrigation. So here we've added kind of another dimension of harvesting. So why would we care about harvesting and infiltration? Well, if you think back to that initial discussion about the hydrology of cities and how they perturb the natural hydrology, there were really two things we had to worry about. One is that we shut off evapotranspiration because we paved over the grass and the trees. And so we'd like to move as much water out of the watershed as the natural state moved water out of the watershed through evapotranspiration. So that's the first thing. The second thing is that by putting that impervious pavement down, we prevented the water from infiltrating and supporting the groundwater and base flow in streams. And so we'd like some of that water that we're running through biofilters to infiltrate to support that groundwater and base flow. And it turns out you can work out exactly how much water should be infiltrated and harvested, and then potentially tune these systems in a distributed way to achieve that natural hydrological balance. So this is what biofilters look like in practice. And one of the reasons I like this set of pictures is because, you know, these aren't the typical engineered structures, right? I mean, if you live in Southern California and you drive along the freeway and you drive over the LA River, it's just it's a concrete conduit, right? There are movies of people having drag races in it. It isn't really attractive unless you like drag races. And this is a very different kind of infrastructure. This is extremely attractive. And so it creates amenities, it creates livability. People want to live in neighborhoods that have these kinds of features. So it's not just about restoring hydrology and protecting ecosystems and creating new water resources. Of course, it is about those things. It's also about trying to create a more livable city. And so that's part of what the water-sensitive city is trying to achieve, a place where people want to live and at the same time live smartly. We're actually running experiments as I speak, in which we're at Monash University setting up mock biofilters in these columns and then trying to understand exactly how plants affect the removal of some of the pollutants that we're worried about, like, for example, pathogens. And so this particular picture just shows you on the right kind of a cartoon of what a biofilter looks like, where you've got the plants and some ponding zone at the top, some fine sand and coarse sand, and then finally a gravel layer. And that black thing there is the tube that the water comes out and would go to, say, your toilet for flushing. So why haven't these things been adopted already? And that's something that we really have to turn to our social science colleagues to understand better. They told us kind of what the context was in which engineers were doing all the work that they were doing over the last 100 years or so, right, through the Hydra social contract. But they also tell us why it is very difficult for people to change the way that they do the things that they do. And one of the terms that's used a lot in the field is this idea of cognitive lock-in. It's the idea that basically there's a cognitive switching cost for changing what we're doing now to something that might even be better for us, but requires changing habits. And in the context of these LID or low impact development technologies, or as they're also called green stormwater infrastructure technologies, the issue really comes down to kind of a reinforcement that happens over time. So you imagine if a city develops around an area, say next to a stream, and cities tend to colonize around streams, that as they build, and then you have the flooding issues that I mentioned earlier, that the stream may become perceived as a threat, right? Because it's what can overflow its banks and then ruin your business and your home, and maybe even cause loss of life. So if the starting point is that we perceive, as a community, we perceive streams as a threat, we lean on our managers to do something about it. And what they do is they turn to the engineers, who basically say, okay, well, what we can do for you is we can move that water as quickly as possible away from the city. And so they change the stream from a natural feature into a hydraulically efficient drainage channel, right? Which has a lot of what we call effective imperviousness. All of the different types of imperviousness are connected to the stream, which then drains very quickly, say, to the ocean. And then now we've converted this, what used to be a really beautiful, potentially beautiful ecosystem, into essentially a conduit, a concrete conduit. it doesn't have a lot of value to us. And so that kind of reinforces this perspective that the stream is a flood or a health risk, and you know, the city needs to do whatever it needs to do to make sure that us, the citizens, are protected from it. And so there's a feedback loop there, which essentially reinforces old ways of behaving, kind of the drained city paradigm, maintaining that drained city paradigm. But you can imagine an alternative world in which, in fact, when people arrived, there were maybe a few civic leaders who had the foresight to say, hey, this stream is a huge benefit. I like to fish in it, you know, and I like to take my kids there, and I like to walk along the banks, or I like to bicycle along it. And so it becomes sort of embedded in the psyche of the community that that stream is a beneficial ecosystem. And then the citizens might lean on the managers to enact policies or infrastructure that works in such a way as to maintain that ecosystem. And so if it's maintained, there's more value, and people are more likely to maintain it in the future. So you have a different feedback loop, which is kind of maintaining the stream in a positive way. And so I think our challenge, going certainly in a megalopolis like Los Angeles or Southern California, where it's kind of a concrete jungle, is going from this right loop where we've got the negative feedback going and the stream as a hazard, to the left loop where the stream is considered as a beneficial ecosystem. Another thing that we can do is exploit the very best technology that's out there. And one of the wonderful tools that's emerging, you know, if you're lucky enough to be alive in this day and age, and I'm sure in the future as well, is this idea of cyber infrastructure. So using computer systems that are linked to you know, valves and control systems, which essentially can, in real time, modify the flow through drainage systems. So the idea here is that we could actually modify our existing drainage systems to protect water quality. And some of these systems are actually being tested in the US and elsewhere. And you know, ultimately it's about making the drainage systems that we have in our cities as smart as the transportation systems we already have, or the food delivery systems. Incredibly intelligent systems that are being, a lot of technology that's being applied to those systems, yet for some reason, maybe it's out of sight, out of mind, we don't apply that same technology to our water infrastructure. So I hope that's a good overview of the project and the presentations to come. I really appreciate your patience listening to me. And if you want to know more about our UCI Water-PIRE, I invite you to have a look at my website and also our Water-PIRE website. And thank you very much.